and then in the afternoon you have your choice of three. This afternoon we'll have, let's see what the options are. We have Cameron Ferris on neuroscience. We have Daniel Shapiro on hazard modeling and related topics. And we have Ivana Bozic on cancer modeling. So a nice variety of topics to choose from, just like yesterday. And with that, I will leave you in the hands of one of the department's very best teachers.
All right. Hey. So, thank you. Thank you. 3 hours of me is a lot. So my hope is that you gain some knowledge, because otherwise 3 hours is like, that's a lot to not gain knowledge. I'm going to dim the lights a little bit to go with. I decided to do this as a, there, is that OK? You can see the slides a little better. Set of PowerPoints and to sort of walk you through this. The first thing I want to do is acknowledge one of my main collaborators in a lot of the work I'm going to be talking about and sort of in developing some of the methodology is Steve Brunt, who's in mechanical engineering. And what we're really thinking about is ultimately the objective here is to think about there's this emerging data science that we're hearing about. Everybody just does a lot of data science these days. You can get a big paycheck off of it if you get good at it. But trying to integrate some of those techniques with more traditional modeling and physics modeling and dynamical systems. Okay, so the idea is that when you have some of these dynamical systems models, we've been using computation now for quite a bit, for quite a long, many decades now, to simulate systems, to look at the dynamics. And now what we have is a new tool in our things that we can do, which is to sort of use some of these data science techniques in partnership with computation, in partnership with modeling, in sort of an integrated fashion to help us do better understanding of things. Okay, so that's the goal. I'm going to sort of break it down to 3 vignettes. The first one is on physical model discovery. This is about taking data and discovering governing equations from that data directly. Okay? So we have some platforms, some ways to do that. The second thing I'm going to talk about is about thinking about coordinate systems. So in addition to the data, I want to think about just because you measured it doesn't make it the right variable. You measured it because you had a sensor for that measurement. Whether it's temperature, pressure, or whatever, it's not necessarily the right variable. How do you start using these data science methods to sort of back out now what the right variables should be? Okay? And the third is just this idea of you don't necessarily get to measure everything. Where would you put sensors? How do you optimally place a limited number of sensors on a system to inform your decision? Now, in practice, it works backwards from the way I'm talking about it. In practice, you go that way. You measure it, better find some good coordinates, then discover physics. But I'm going to talk about it this way. Okay? All right. So that's going to be the goal of this morning. The first part, the physical model discovery, I'm going to do that up front for the first session. And then we'll have a little coffee break. And then when we come back, I'll hit the other 2. OK. Any questions on that? Everybody's good? Like, raise your hand as we're going along if you have any questions. And I'll ignore you. I mean, I'll be nice and say, yeah, question. OK. All right. By the way, here's where I like to start. The first thing you have to ask when you're going to go about doing data science is, what's the nature of data? OK? You cannot just generically say, I took my data and I trained a deep neural net. OK, you can say that. And a lot of people do that, exactly that. I just throw it into a deep neural net, get some stuff. This is kind of like the wrong thing to be thinking about, in my view. Right? One of the things that's happened with PyTorch, TensorFlow, it is trivial to train a neural net. A few lines of code. Throw your data in. Get some stuff out. Say, hey, look, I understand. I don't know if you understood anything. Do you understand things? This is one of the things we want to ask about is when you're going to try to do model building, it's going to be very important for you to understand what you're doing with this. And in particular, you have to start thinking about what's the quality of your data. How much noise is on that? When you take your measurements, How good a sensor do you have? Different applications have very different qualities of sensors. What's the quantity of the data? Okay? There are limited things you can do when you are limited in the data you can collect. For instance, I have some friends in biology, and they go, okay, we got all this data, and they're trying to look at cell development, let's say, and I got all this data, and I got 5 time points, day 1, day 10, day 20. Like, there's massive gaps in your data. So they might have a ton of data at day 1. But you have no idea what happened between day 1 and day 10. And it turns out a ton happened, right? So you're very limited in what you can think about saying about the time course of cell dynamics. Observability. This goes back to the fact that just because you measured it, it might not be the right variable. You're measuring something in the system, and what you're really after is what can I really observe out of that system that's there, even though I took a measurement of maybe something else, okay? And I highlight this one in orange, because to me this is one of the most important issues to deal with up front, even after all those issues, which is, are you going to interpolate or are you going to extrapolate? If you take your data and put it into your machine learning algorithm and you get amazing performance, probably you're interpolating. In fact, I put money on it, okay? So interpolation is something that is very different than extrapolation. Extrapolation, I collect data for a little bit. Extrapolation is say predict the future when I have no data in that future. Okay, that's a true extrapolation. By the way, the entire, let's call it data science industrial complex that we live in here in Seattle, right, which is Facebook, Google, Microsoft, Amazon, right? They're all sitting there. What they tend to spend a lot of money on is making their data science problems interpolations. Right? So how do we get self-driving cars to work so well? You annotate thousands and thousands and thousands of hours of video by hand to create a car where the entire world it sees is actually an interpolation. Okay? Now, when you miss that, when you have data that's not, the training data does not span the real world, is when you have problems, right? So you have a car that was in Pittsburgh that killed somebody last year, and that was partly a situation where there was no training data to talk about a person on the side of the road running with their bike, carrying it at night, right? That wasn't in the training set. So there was a gap between the training data and the real data, and this is where you have problems, okay? But the goal is to go towards interpolation. Now, a lot of science, what we're actually going to have to do is this, extrapolation, okay? There's no 99% correct in this world. Okay, so I want to set the right framing for your expectations that this you're going to try to do a good job with, but 99%, that probably means you're interpolating without you knowing it. Okay? All right, so I like to set this up because I think these are the first questions you ask about your data set. You can't just blindly start applying techniques. Once you can answer some of the questions, what's your net quality, quantity, observability, then you start picking techniques to use, okay, based upon that. All right, here's the mathematical framework I want to discuss throughout the entire morning. Here it is. What I have here is a dynamical system. It could be, any kind of physical process or engineering process. It could be fluid flow. It could be electrodynamics. It could be quantum, whatever it happens to be. dx dt equals f is some equations of motion that you have that is your system. In other words, I'm going to collect data from an underlying physical system that has dynamics. Okay? I'm not looking at customers and a database of customers. I'm not looking at things that are not physics-based. I'm going to focus on things that are, let's say, physics-based. They have governing equations. And those governing equations are described by x. By f. X itself is the state space. Okay? Now, f itself can be time-dependent. Typically, it has some parameters, which let's call all the parameters that are there theta. Like, for instance, in fluid flow, you have a Reynolds number. So that would be one of your parameters that is there. You may even have some stochastic effects in that model. And so this model here typically is given to you, right? So go pick up, you go to library, you go look up any application area, and go look at the shelves, and you pull out a book, and it tells you what the dx dt is. Here it is. Here's your governing equations. And then what we do, and we've traditionally done, is we simulate that, right? And we get some understanding. We can improve the models as we go along, okay? So this is our dynamics. But what we're really going to do is we're going to actually measure a system. Here it is. Here's my measurement. I measure it at certain time snapshots. Y of t of k. So I get a collection of measurements. By the way, I'm measuring it. I don't necessarily measure x. I measure a proxy of x through some measurement model h. Okay? So I don't necessarily have access to the actual state space variable. Now, if I did, then h is the identity. Just x and y are the same. Okay? But I'm measuring something of this state space, and every time I take a measurement, it's imbued with some noise. Okay? No perfect measurements. I have noise on my sensors. I have something, I always have imperfect measurements. Okay? Now, here's what we're going to do. We're going to basically take this problem and say, you don't know what f is. You don't know what x is. You don't know what h is. You don't know what theta is. Like I'm taking everything away from you. The only thing I'm going to give you is y. Here's what your sensors say. And from that, your goal is to back out the rest. I want you to give me back h. I want you to give me back f. I want you to give me back thetas. All of it. Okay? Now, first of all, this is an impossible problem. Now, in math terms, it's called ill-posed. Okay? So ill-posed means basically you can't solve this. What I'm proposing to you is just ill-posed. There's no way you can do this. Unless what? The way we solve ill-posed problems mathematically is you make assumptions. Okay? Assumptions, or making assumptions of this form, in this machine learning world called regularizations. Okay? That's it. So you're going to make some assumptions. Assumptions are going to equal regularizers. You talked about regularizers. Okay? So this is the game. I'm going to take a problem you can't solve. I'm going to be able to solve it by imposing regularizers. Okay? Everybody good with that? That, in some sense, is the ultimate goal in the data science. Go after some regularizations, and with those regularizations, I'm going to be able to get some solutions out. So there's extreme pressure on the regularizers. If you want something that's going to come out to make sense, that means you've got to make some good assumptions or some good regularizers for yourself. Okay? All right. So, one second here. What's going on there? Okay, never mind. Got something on my screen. Everybody good with the goal? Solving the impossible. No problem. So let's start with model discovery. So this is part one of what we're going to talk about, which is model discovery. And for the moment, I'm going to go ahead and say that my h, my measurement model, is the identity. So I'm going to assume, to begin with, that I can measure the state space. Okay? All right. So the idea here is to say I'm going to take measurements of the system, and I'm going to tell you what the governing equations were, just from the data. Okay? That's going to be our goal. The mathematics of this is all going to come down to this. This is the whole morning. Ax equals b. There's no fancy math here. Now, I used to think I knew a lot about ax equal to b, right? Because you pick up a linear algebra book, you spend all this time ax equal to b, and now here's the big lie about linear algebra. And if you look at your textbooks in linear algebra that you took, that I took, that I probably taught, I know I've taught some of you linear algebra, so some of you are in here that took my class, right? What do we cover? we tend to cover like n by n's, square matrices. I have n equations, n unknowns, go solve for them. And you know what? The only thing you've really got to watch out for is when the determinant is 0. Otherwise, you're good, right? That's it. That's not linear algebra of today. In fact, kind of really outdated. In data science, matrices are not square. When you collect your data, typically these matrices are going to be of this form. They're going to be really tall and skinny or really short and fat. You are massively overdetermined or underdetermined. Now, from your linear algebra, we never covered it. Why? Because in one case, there's no solutions. In the other case, there's an infinity. So what we do is just say, like, tell you what, let's just stick to square matrices where the determinant's not 0, and let's keep working on that. So you never really come back to this to really come after this. But in some sense, that's what we have to live with is in the data science world, those are the matrices we have to work with. AX equal to B. Massively over and underdetermined. No solutions or an infinite number of solutions. And of course, you could ask, well, what's the problem? Because I just put it in MATLAB, I hit backslash it. I get an answer. Right? I don't have to think about it. So what are you going to have to do? The only way we're going to solve this problem here that has either no solutions or an infinite number of solutions is you're going to have to make some assumptions. In other words, you're going to have to impose a regularizer. Okay? And in fact, in MATLAB, I give you some commands that are all AX equal to B solvers. Here they are. There's the backslash, pseudo inverse, lasso, ridge, elastic, robust fit, and there's more. These are just like off the shelf. You just put A and B, get a solution out. Each one of these is making a different assumption about the regularization. It's the only difference between them. Okay? And so we're going to dive down on that a little bit and talk about what's going on with that. And remember, this is just AX equal to B. Keep in mind, that's the only thing I'm going to talk about for this first session, is AX equal to B. Okay? But I'm going to set up some very special AX equal to B problems for me, and hopefully for you too. Okay? All right. Any questions on this? So far, so good? Anyway, for those of you who become pro-level, you know, that means like professional educators of some sort, down the road in your life, and you teach a linear algebra course, do your students and yourself a favor. Don't just teach square matrices. Okay? Start teaching people like, okay, yeah, there's this thing called a square matrix, but nobody does it. Here's what we really do. They're like this or like this. Let's get to that, because that matters now. Okay? All right. So, as I said, this is what we're going to deal with here. AX equal to B is subject to something. So I'm going to impose some kind of constraint or regularizer on this thing. A lot of times, I always think about this as framing, right? So this is what I want to do here, and I'm going to frame this way for either over or under determined systems. And by the way, the more general framing of this is here. Right? I don't have to constrain to a linear system. I could make a nonlinear system, some kind of thing I'm trying to satisfy with some subject to line. So another way to think about it, it's all about F and G. Right? F is what I'm trying to satisfy. G is going to be my regularizers. A lot of times, here's I guess what I've evolved towards in my own thinking. A lot of times we think about F is important. This is what I'm trying to satisfy. But all the magic happens in G. Everything's in G, in my view. Like F is whatever. G is where you can start putting structure in. G is going to carry the day. Okay? Even though F is obvious. Maybe that's the way to say it. Of course, I'm trying to solve this. What's not obvious is what G is. If you make some good G's, good things can happen. So maybe one way to say it is that in fact, I would say this is the full summary of all of machine learning. It all comes down to this, all of it. You can make that a neural network up there. Neural networks have all kinds of regularizers. Maybe you've heard things like dropout, right? That's one thing to do with your neural network. You can do all pruning, like all kinds of regularizers that you put here to train a neural network. And then if you get a good result, you write it up and you get 10,000 citations because everybody uses it. All the magic's there. That's obvious. This is not. Okay? One slide summary. Now you know machine learning. We could just stop here. And I would say go party, but it's raining out. So we're just going to stay inside, right? Enjoy the rain. All right. So real quick, this is what we're going to talk about, though. I just think that's even too hard right now. We'll get to this a little bit in the next sessions in the afternoon, or later in the morning. So here's what I'm going to go with. Let's go back to this governing equation. I have state measurements of my system X, and it's some nonlinear dynamical system. Okay? So what I want to do is I give you measurements. I want you to tell me what was the dynamics of that thing. I don't know what it was. I don't know what n is. And again, like I said, most of the way we're educated is we're told what n is at the beginning. If you're studying Maxwell's equations, you know, in E&M, it's like written down in the book. This is your right-hand side. Every single application area, whether it's heat transfer, electrodynamics, quantum mechanics, we're told what the governing equations are right at the beginning, and then we simulate it. Here, I don't know what they are. What could they be? Well, we have a lot of knowledge that we've built over a long time. We know canonical things like there's diffusion in systems, there's dispersion, all kinds of things that happen in physical systems. So if you go pick up from the library again, any book on the sciences, you look at the governing equations. Here's the one thing that's common about all of those fields. All of those fields, the right-hand side has just a couple terms. 2, 3, 4. Very rarely do you actually have to make a page break to the next line, right? Maxwell equations are 4 PDEs. You can write them down. Pretty concise. Quantum mechanics, Schrodinger equation, F equals ma. Go through. Fluid dynamics, you have Navier-Stokes. In all these examples, in characterizing these complex systems, there's just a few terms over there. That is my assumption that I'm going to be making. That is my regularizer. Okay? So remember, when I say assumption, you say regularizer. It doesn't roll off the tongue, really. So we could get this crowd hopping, right? I know it's only 9 in the morning, but okay. Everybody good with that? That is the important thing I'm going to bring to the table. By the way, this gets us to some philosophical pictures about how we've developed models in the past. We think a lot about the idea of parsimonious models. In other words, the smallest number of terms that are representative of the full dynamics. This is why a lot of our textbooks have these canonical terms, very few of them, and yet they seem to characterize the very complex systems. Okay? So parsimony is what we're after. Few terms. So the question is, what could that right-hand side be? Well, I'm going to make a library of potential right-hand side terms. So theta is a library. And in this library is all my knowledge of what I've seen in right-hand sides before, potentially. You could have constants on the right-hand side. X, remember, this is an n-dimensional state space. So the x there really represents all the linear terms. xp2 is all the polynomials of degree 2. So that one, for instance, can expand out to here. I can put polynomials, sines, cosines. It's only limited by my imagination. Okay? So I build a giant library. Every single column of this library is a different potential right-hand side term. And every row is my measurement of the system. So remember, I'm measuring x. So if you give me measurements of x, I can build the library. Every row is a time snapshot. Generally, this will have, I might have 1,000 different potential right-hand side terms. And I'm going to measure in time for a long time. So this is going to be it's going to be a tall, skinny matrix is the way I'm going to set this up. This is the matrix A in AX equal to B. Potential right-hand side terms. Okay? What do I know? Or what am I going to impose? What I'm going to impose about this library is, well, I made up this massive library, but I know for any system I measure, there's only 2, 3 columns that should matter. If you just look at our canonical knowledge of physics and engineering principles, I would challenge you to find any course that had more than 2, 3, 4 terms on that right-hand side term. Occasionally you do, but you kind of like, oh, whatever, that's super, right? But most part, you have a few terms there. And this is what the assumption I'm going to make here is out of all those thousands of library terms, there's like 2, 3, 4 columns that matter at most. Okay? That's my assumption. Okay, so let me give you an example of this. Here it is. This method is called the sparse identification of nonlinear dynamics. So what we're going to impose, this AX equal B solve, is we're going to promote sparsity on the AX equal to B solve. Okay? So what does this mean? Well, I'll show you here in a minute in this, how this slide works. So I'm going to take a system. Here it is, the Lorenz model. I'm not going to tell you what it is. I mean, you can see it, right? So I don't have to. But suppose I just gave you the time series. Here's X, Y, and Z. I just give you 3 time series and say, hey, check it out. I took measurements of this system. Here's their time series. Your job is to tell me what governing equations generated that time series. Okay? So the way we're going to do this is if you give me X, Y, and Z, I'm trying to find a model X dot equals f of X. X dot equals f of X. X dot. So, okay, first of all, if I have that time series then, I need its derivative. So what I'm going to do is take X and Y and Z, differentiate it to produce X dot. Okay? State space derivative. That is the vector B in AX equal to B. So what I've set up here is there's the derivative. That's going to be the B. Here's my library. That's A. AX equal to B. Now, what I could do at this point is just say, like, I have an X. I just have to solve for this X, which are the coefficients of each of the library terms. Okay? That's what that is. So I'm solving for is that. It's like, okay, so I have the derivative. And that derivative has to be basically fit by this library. What is the coefficient in front of each library term? I could definitely just backslash it at this point. Now, backslash is a least square fit. So how do you make least square penalties go down? You make everybody small. And if someone's small and you square them, they're even smaller. That's how you get a good L2 score. Okay? So if you hit backslash here, it would say, hey, all you library terms, you all matter just a little bit. You spread it out over the whole thing. So every single term in the library basically contributes to this. What we want to do instead is promote sparsity. We're going to say, no, no, no. Only a few of those library columns actually matter. So I'm going to do AX equal to B and say I want the sparsest solution possible. In other words, I want everything to be 0 except for a few terms. And how do you do this? Well, one common way to do this is through what's called lasso. Okay, the lasso is a way to solve AX equal B and promote sparsity. Turns out lasso kind of sucks. Sorry, I'm on the mic, right? I'll say it again then. Sucks. Yeah. Everybody kind of knows it in practice, actually. Like anybody who uses lasso knows it kind of is like not that good. It's morally the right thing to do, right? But it's not practically a good way to do it. But we want to promote this sparsity. And the way we actually do it in practice here, and I'll mention some other techniques a little bit later, is we just do sequential least square thresholding. So we do the backslash because it's so easy. But then what we do is say anybody who's really small below a threshold, throw them away, do it again and again and again, and only keep terms that survive your threshold bar of cutoff. And what happens is when you do this, you see where those red dots are and the blue and the green? That is your solution. Everybody else is 0 except for those. Those survive. And those that survive turns out to be the columns. It gives you back exactly the model you started with. So through this sparse regression process, it says, here are the columns I need to reconstruct this, and the columns it picks out correspond to library terms, and it picked out of the library, by the way, here are the governing equations, and it turns out it's exactly what you started with. Okay? So that's the way this thing works. You build the library, you pull out the terms, you got yourself your governing equations out of this thing. Yeah? What is bad about lasso? Okay. Hold on. this thing is not a, I'm going to do this. So lasso tends to make a lot of mistakes early in what's called the lasso path. As it starts to eliminating variables, it'll make a lot of mistakes up front, is one way to think about it. In fact, Kendez and whoever else wrote a paper about this in 2017. So you don't have to just trust me. You can go right to Emmanuel Kendez, who's, you know, he's an important dude. And you can just read his paper, and you can just see that lasso has problems. So what a lot of people do is they don't do lasso straight up. They'll do lasso maybe. And if you add, you'll do elastic net, you'll have a little bit of a L2 penalty to try to stabilize this lasso. But this just works better than both, I think. And I'll talk about one other innovation we have on this, on sparse regression, that we've been working on with Peng and Sasha as well. So that's the thing. When it's a variable elimination problem, and if you start eliminating the wrong variables up front, there's no way you get the right answer. Yeah, that's one way to think about it. By the way, one thing to make this happen is you have to make sure to produce good derivatives. Producing good derivatives is hard. Numerical differentiation is a difficult task, especially with noisy data. Okay, so if you try to use finite differences here, you'll get awful results. So you need to use a little bit higher end differentiation techniques. We use TB-diff. It's a total variational derivative. Helps smooth these things out, and then you can differentiate it. Let me just show you an example of this. You can handle a little bit of noise in this thing and still get the right answer. But noise is an issue, right? You want to do data-driven discovery. As soon as you start having measurement noise, it's really going to affect your ability to pull out the right governing equations. I'm going to talk a little bit more about this in a moment, but this is sort of, you know, in the standard way we have it, this is about as much noise as you can tolerate, a few %. Now, this was a simple model. Let's go to something a little harder. This is flow around a cylinder. This is like a classic problem in applied math when you get flow coming past the cylinder, you get von Karman vortex shedding off the back end. And so what I have here is my state space is big, right? It's all the XY positions of this fluid dynamic system, which might have, it might be a 1,000,000 degree of freedom system, okay? So it's a really large system. However, what is known about this system is if you look at this system and you look at the low dimensional structure in it, so you could do this with standard just singular value decomposition, or which is PCA, you find that there's 3 modes that dominate the dynamics. And there you are. So you got some modal structures in there. And these are sort of all the dynamics that you'd see in this shedding of the vortices is actually driven by these 3 modes. Okay. So what you could do with this is if you do the SSVD, the V matrix tells you what those 3 modes, spatial modes, are doing in time. So you say, okay, I'm going to take the time series of the V and say, what are the governing equations then in this low rank subspace? If you do that, this is what you discover. Here is the dynamics of those 3 modes. And what's interesting about this, we just took the data and did it. And you get this model. And this is a model that was sort of 30 years in development. There was some idea about like, well, you know, when you measure fluid flow, the Navier-Stokes is quadratic. And yet, the kind of instability it's producing, which is this cubic dynamic, this periodic dynamics, is like a Hopf bifurcation, which is cubic. How does a quadratic thing produce a cubic? Right? So this was proposed as a route to turbulence way back in the early 70s, and all the way to here in 2003. So you got a 32-year gap before I say, okay, we actually know how this happens. Careful asymptotics, you find that there's a slow, fast scale dynamics that interact to produce this cubic. We just regress on the data, pop that out immediately, right? So we can discover that physics very simply. You can also do other kind of models like this. Here's a different type. These are implicit, we call this implicit SINDI, because now if you have equations of this form here, right, where you have a numerator and denominator, the problem with this is if you try to build a library off here and you try to say what are the terms there, it's not structured to handle that, right? Because that actually has an infinite series expansion on the right-hand side. So we'd have to basically figure out how to handle this. And the way you can't just multiply by FD on that side, move the f of x over and regress, because what we'll say is like, oh, it'll try to make everybody 0. It just says, how about 0 times this is equal to 0, I've satisfied your problem. So instead, what you do is you bring it over and you look at the Sparse's vectors spanning the null space of this AX equal to B. So it's the same process. This is super brittle, in fairness. But the idea here is that you can handle a much broader class of systems, in particular things, for those of you who are in whatever, chemistry, biology, or biochemistry, these Michaelis-Menten models where you start having these equations of this form. So this here is the kind of structure you would do this implicit Cindy model. By the way, this can almost tolerate no noise, because what ends up happening if you have a little bit of noise, we're trying to find the Sparse's vectors that span the null space, but your null space just becomes garbage with noise. We have a better technique to do it now, which can now handle some noise on this thing. Okay? All right, so here's the question then. So what we're after here then is trying to recover governing equations from data, right? That's what I'm showing you we can do. And it does bring around this idea of Occam's Razor and parsimony. These are kind of ideas that are, and sometimes old as the hills. William of Occam is in the 1200s. He's already talking about this idea that the simplest explanation is probably the right one, right? He's already, or the simplest thing that satisfies some the simplest hypotheses that satisfy what you observe is probably what you stick with versus adding more and more complexity to your explanation. So this is an old idea, right? So this is, not everything was dark in the dark ages. There's William of Occam, Nathan of Seattle. That'd be an awesome name, right? We could just walk around, I'm Nathan of Seattle. And they're like, who else is Nathan of Seattle? There's another Nathan of Seattle. And filming, for instance, we'd have to figure out how to do that. Like, well, I live in the University District, so I could be Nathan of the University District above 18th Street, or, But here, maybe not that many people, and you could call yourself the one guy from Occam. And here's what the idea was, is this idea of parsimony. And what you start thinking about is this of model discovery. So when you write down a model, of course you want your model to have low error, right? Remember the F. I want this thing to satisfy my hypothesis or satisfy the data. So I want a low error in prediction or reconstruction. So what you see here is the error versus the number of terms in my model. Okay? And what you start to see is like, okay, so the simplest model I could give you is dx dt equals 0. You can assume your model is a constant. Now you can imagine your model error is going to be pretty big, right? So you say, okay, that's about the biggest error I can get is if I have basically a constant to describe my dynamics. But as I add more terms, now it starts to hopefully fill in what the dynamics are doing, and my error starts to drop. Now here's where it gets interesting. As I add more and more terms on a training set of data, I could use each extra term to help me push my error down. Okay? So you start to drop, and at some point it starts to flatten out, and your error will still keep going down. But when you get over here in that region, if you look at now not the training set but a test set, your error starts to go back up because now you're in the land of overfitting. Okay? So that's what this thing is telling you. So this idea of parsimony comes right to this idea here where this is what's called the Pareto front. And what you want to do is find a solution on that Pareto front. You would like to evaluate this. And in fact, in the 50s already, people were talking about this Kullback-Leibler divergence, which is to say, if I have a model that I built and I have the data, what's the statistical distance between them, right? So this KL divergence told you how far apart the model and the data are. This was later generalized in the 70s. In fact, let me show you. Here's the references. Akaike did this AIC, which is an information criteria which measures that among a set of models, which one statistically is closest to the statistics of your data. Okay? Generalized a Bayesian information criteria in 78 by Schwartz. And really the assumption here is if I give you a limited set of models, I come up with a bunch of models, and I say, which one is it? I can compute these information scores The one with the lowest one wins in some sense. And by the way, the information scores, let me go back a slide, is basically penalized by the number of terms. So this is an important piece of the parsimony. Every term you add will cost you. So if you just keep adding terms to push your error down, you're actually being penalized from an information criteria point of view. Okay? So that's why you also get this rise up there in that slope. And this is meant to present overfitting. Okay? And that's a real problem with modern neural nets, by the way, is the overfitting idea. By the way, I should guess make one other comment here. So if I give you so much data that you're really in an interpolative setting, right? Then it's not even clear overfitting is a problem. Because what I mean by that is this. If I give you all possibilities of data and I say, okay, here's some new data, but the new data really looks like all your other data, it's not really living outside of that space. You're going to do a great job with it. So you can basically overfit by overtraining. And actually, I think this is the way a lot of these modern neural nets are doing. For speech and image, you have so much data that like overfitting is not even really the issue, because overfitting is only an issue if you try to predict data outside of your training set that really is different. But if your test set is really not different, you're fine. So just as a ballpark figure for this, if you pick up Bengio's Goodfellow's book on deep learning, right? Actually, you can download the whole PDF. It's online for free. There's in there somewhere they talk about how much training. If I wanted to teach the neural net to, I have an image classification. I want to teach it to recognize like a white Toyota pickup. How many training samples should I put in? They estimate about 5,000. So here's what's interesting. 5,000. If I made this a class project for today and said, okay, we need 5,000 pictures of Toyota pickups. Now each of you would get like, okay, once you get to 50, you're like, okay, like I've kind of got every possible angle. Maybe I could wait till night to take some pictures too, but how many ways can you view a Toyota pickup? So 5,000 is like, I've seen it in every possible way. So if you give me a new one, is it really new? Because I've got 5,000 pictures. So I'm pretty much sure that one of my 5,000 is going to be there. Do you know what I'm saying? So I could think about it as an overfitting, but if I train on so much data, right? So this is an interesting concept around overfitting. I want to make sure we understand overfitting and overfitting in some of these big data problems. So the nice thing, by the way, here, coming back to this model selection, is this sparse regression framework allows you a very efficient way to do, you can tie it into information criteria, which is when you do this sparsity promotion, you actually, what it can do for you is if you run a bunch of models, it will basically start to downsample how many of these models live near the Pareto front. So normally for information criteria, this would be a combinatorial large problem to look at, but the sparse regression just gets you, here's all the models that live near the Pareto front, and then now I have just a handful of models that I can run and compute AIC, BIC scores and select models that have strong support, no support, weak support. So there's a nice tie-in from this kind of methodology over to information criteria and model selection as well. Okay? And again, it's kind of a sanity check across validation of sorts. You can also move this into spatial temporal systems, discovering PDE. Here's Sam Rudy. So Steve and I have been working on this for a while, and we took a big hit this year because we had like Sam just graduated. I'm going to talk about Kathleen just graduated. Krithika graduated. Bethany left. Like all of our talent pool is like taken off, right? So it's super sad for us because we don't have it. They have all the talent. So now we have to get new people in with talent. I think Pung's leaving. Like, it's sad. I mean, I know you got to grow up and get a real job and stuff, but I think we're pretty fun to hang out with. It's just the eternal postdoc or a grad student, right? That's something, right? Isn't that something? Okay. Well, anyway, here's Sam. Apparently, he wants to leave. But he did this amazing work on discovering PDE. So you take the same architecture, and now you measure spatial temporal systems. And now your library doesn't just include possible right-hand side terms. It includes terms that have spatial derivatives. Okay, so I have a diffusion over here. I have x derivatives, y derivatives. nonlinear versions of these, just a bunch of columns. By the way, this AX equal to B is huge, right? Because now I have a full PDE. So if I do that system with 1 million grid points, that's my state space, okay? And I've got to now start doing AX equal to B on a much bigger matrix, okay? But same philosophy. You just simply say, construct AX equal to B. Solve. And what you end up doing out of measuring fluid flow is you actually find, here's your identified equations, Navier-Stokes. All I did was measure that flow field, and I wrote down Navier-Stokes. Now, Navier-Stokes we derive through pillbox derivations, conservation of mass, momentum, things like this, and we come up with this equation. Here, you just get it directly from measurements. Those are the two terms that explain that data, right? Now, the nice thing, too, about systems like this, there's a lot of low-dimensional structure there. And what this allows you to do is massively downsample to make this AX equal to B much smaller. So what you're simply doing is doing row sampling. And you can still get the Navier-Stokes. OK? That's what you do to PDEs. There's a couple of important things to think about. You can also do it in what's called a Lagrangian measurement system. What if my sensor is moving with the dynamics? Right? Where does this play? Well, play a role. Well, if you drop a sensor in an ocean, it's not going to stay still. Right? It's going to flow with the dynamics. The question is, if you had a situation like that where you place a sensor in a system and it moves with the dynamics, could you still discover equations? Yes. So in here, what we do is we have the random walker. We attach a sensor to the random walker to see where they're going. We have a bunch of trajectories. And what we can do is regress down, and you find the heat equation. Now, this is a very well-known result. But it's nice as a sanity check that you can do things like this. The other thing you have to worry about is disambiguation, which is if you saw a traveling wave move across the room from left to right, there's so many models that can produce a traveling wave that moves left to right. I could write down 10 immediately. It's like, here's 10 models that will all produce a wave that moves from left to right. So when you do the regression to find the most parsimonious, it would say, hey, you know what? If you see a wave moving left to right, that's the easiest model that will do it. One-way wave equation. So if you want to, if that's the case, you don't know if that's the case. It could be a bunch of different models. So the way to do it is put in different initial data with different initial amplitudes. So for instance, if I gave you that data, where there's two different waves moving there, and that bigger one's moving faster, there's no way that the one-way wave equation is consistent with that. So it says, actually, what's consistent with that is the KdV equation here. Okay? So by putting different initial conditions into your system, you can disambiguate from having models that can all produce similar-looking phenomena. And by the way, this is here's a bunch of canonical PDE models. I don't know what everybody's background is on PDEs, but from KdV, Berger, Schrodinger, nonlinear Schrodinger, Kuramoto-Shevchinski, reaction diffusion, Navier-Stokes, we can get them all, right? So for us, of course, this is simulated data, right? So we simulate the data. I just give you the data and ask, can you back it out? So it's a proof of concept piece at this point, and we want to, of course, take this out into the field for systems. We did one experiment. Here's the experiment. All right, this is in Steve's lab. Drill a hole in the wall. Make a pendulum. Do you see that little blue there? You see that? Can you see that a little bit? It's lit up blue. Maybe it's too far back for you. So this experiment was done. And by the way, I love the state school style here. It's like off-white cinder block with off-white linoleum floors with off-white, those tiles that you throw pencils through, right? And we're doing world-class science, okay? So all of you from the UW, go Dubs, okay? There we are. So we have this experiment, and here's what we did with it. I don't know if you saw it, but attached to the end of that pendulum was a little Arduino. And that Arduino just broadcasts its accelerometer readings, okay? And when you do that, you get data, and there's the data off that Arduino. So this is a real experiment. And you say, OK, let's try this. Let's go ahead and regress, do this Cindy regression, set up AX equal to B, promote sparsity. And what do you get out of this thing? Well, here's the output from the Python notebook. dx naught dt is x1. dx1 dt is some small number x1. That's the damping. Some number sine x naught. It recovers the pendulum with damping. OK? So nice. We have this example where it's like you take real data, discover what you knew was supposed to be there. Interestingly enough, if you don't remember some of these pendulum went over the top, you have to have some that go over the top. If you don't do that, if you just have big swings, it will say, well, that looks like an x cubed or an x fifth. Once you go over the top, it says, whoa, there's no way a polynomial can do that. It puts in the sign. OK? So anyway, maybe you're not impressed with that, but we were super excited. You know what we started with? And I have a whole nother storyline along this. Is we first started trying to just drop balls out of the, actually, if you go over to the Gates, Allen Auditorium here next door, you know, the tall thing. So Taryn was over there at night with this styrofoam ball with the accelerometer in it and dropping the ball from the top of the 6th floor and then taking the elevator down and collecting it. And it turns out, this is a whole nother story, but ball drops aren't F equals ma. The wind resistance on that is so much that it really, it's like, so anyway, we just we're going to put up a paper in the archive that you might like reading, and it's about ball drops, because we came back to this experiment. And it turns out there's almost no way Galileo could have said gravity's constant from measurements. Because you look at the measurements, it's like, that's a super leap. The data does not back up his viewpoint at all. Just a comment on the side. Anyway, super fun. So we moved away from ball drops, because he had to do it late at night as well, because you know that way you don't have targets on the bottom. And we moved to this, drilling holes in the wall, and it worked. OK. Let me keep going down this road, and I want to talk about discrepancy models. So what do I mean by discrepancy models? I'm going to build on this theme. Well, so far what we've said is I have measurements of a system. I don't know what produced the governing equations, so I'm just going to solve this AX equal to B with sparse regression. And oh, look at that, I got my physics out. Yes?
Can you comment a little bit about computing the derivatives if your data is very sparse time-wise?
Oh, that's a good question. So if your data is very sparse time-wise, I cannot comment. Oh, OK, actually, what would you do in practice? And this is where it gets a little dicey. So for the PD example, some of the ways we smooth data out is through local splines to smooth it first, then take derivatives. The problem with that is if you have pretty big gaps in your time, then you're going to have to make some assumptions about what you fit in there. You could do like a compressive sensing trick to fill it in with some smooth functions. You could put splines through, but now it's not clear how much you're missing, right? And that's a problematic piece, actually. It's also the problematic piece for the biologists who say, I've got 5 time points, right? And you're like, it's really hard for me to build a model of time dynamics with 5 time points of day 1, day 10, day 20, when there's this massive gaps. So. But you know, it'll be interesting to see how that evolves over time, because I think one thing that's happening is I'm always amazed at what people can measure. So measurement is this really important thing that's happening in the community. So part of the big data-driven revolution, right, is just things like this. This phone, right, this is even not a very good phone, right, HD camera in front and back. They're less than $1 a piece. Like these used to be kind of expensive. Now they're dirt cheap. They're commodity. And you can sit there and you can collect data off of them. This is sensor technologies. You can buy laser pointers, right? I got a bunch here. They're less than $1 in Hong Kong. I mean, they're more expensive here with markup, but in the streets of Hong Kong, I had these for $1. A laser for $1. Like, how impressive is that? Because, you know, the laser is only just a little over 50 years old, and now you can buy it for $1. And these cameras, less than $1. But at the end of the day, they both are the foundations of measurement technologies and tons of data. You can just collect data. You can put it in biology, neuroscience, whatever you want to do. This is where we're kind of headed, is like I'm going to give you terabytes of data that I can collect in an hour, go analyze it, right? And we'll talk more about that later. But that's part of what's happening. So eventually over time, hopefully people can close up the gap in time series that way too. So by the way, what are discrepancy models? Well, you know, we started with, I said, I didn't know anything about the physics. Well, that's probably not true. You know, normally I have partial knowledge. I know some things are true. It's just that my model is probably not good enough. So I'd like to do some discovery there. So the idea here is I start off with my model. Let's call this the Platonic model that I have, right? The idealization of the model, like F equals ma. This is, for instance, if you started off with Newton or Galileo, you'd say, like, look, this body just falls under gravity. But then you take measurements, and you're like, okay, that's totally not true. Like, what I see in the data does not match what the model says, and not in a way that, like, oh, I have some noise. It's clearly not just some Gaussian distribution of noise on this thing. It is something you're missing, right? In a falling drop, it's this idea of wind resistance, mass displacement as the ball falls, things like this. So what you'd really like to do is say, but look, I've got a whole degree, advanced degree, doing science stuff. So it's not like I'm not knowledgeable about some things. I actually have some knowledge, but somehow my knowledge or my Platonic ideal of that system I'm measuring is not good enough. But can I just do a regression on this? So this is still ax equal to b, just as it was before. It's just that now, since I know this, I can bring it over to this side, and it's part of b now. Okay? So there's no change, except for that I can now enforce known physics that I know is there. So here's the model we're going to do. I'm just going to show you, get right to the punchline. Here's a double pendulum on a cart. And this is in Steve's lab. And this is kind of a fun little experiment. And the goal of it, that cart, is to stabilize the pendulum, this double pendulum, in the upright position. And you can see it does it on the bottom, but not on the top. So let's talk about the difference. The top. The idea here is that you imbue that little cart with known physics. And the known physics is, you know the masses of these rods, you know where the center position is, you know how long they are. So it has a perfect Platonic model of a double cart pendulum system, right? So that model there, it says, I know what the physics is. And it says, I'm going to stabilize it. And it can't. What you really want to move towards is this idea of saying, well, so what's off? Well, first of all, there's nonlinear frictional air resistance there. Each of these bearings has a little bit of frictional forces as well, probably nonlinear, maybe linear. The point is, the cart doesn't know about that. Now, the moment you teach it, let it teach itself. Let's say, like, here's my model, but for my measurements and my model don't match up. I want to take those discrepancies and start building the model for what I'm missing. And the goal is then to do this, is to put that in there and to have this thing say, now with my improved model, which is the real physics, I can do this kind of thing here. Now, why is this important? I think actually this is probably the most important application of this stuff, because when we move over to things like this, let me start the video. Okay. This is what's called the digital twin. So this is actually happening quite a bit in manufacturing, is we're trying to build models like this, where it's a very simple thing, right? It's just some rods, some twist parts. And I want to build a virtual model of it. That's going to be my digital twin. I'm going to put this on the factory floor. The problem with it is that doesn't quite match that in practice. It's off just by a little bit. But imagine a factory floor where it's going through all these robots, all that are off by a little bit. What do you think you're going to come up with at the end? Something that's off by a lot. So your physics, ideally, that's there is very different than the physics that's actually there. Not very different. Off by a little bit, potentially. So what you really need to do is imbue these guys with the ability for a discrepancy model. And by the way, every single robot you build will have a slightly different discrepancy model. This robot has a little bit more stick right there. than another one that just got oiled or whatever. I'm just making this stuff up, right? But you know what I'm saying, right? Every single one will be unique, and what you want to have is this platform that says, here's your ballpark physics, gets most of it. What it needs is the learning module on top of it to sort of make adjustments. Understand how to build a model that says, for me personally, here's my discrepancy model currently. And by the way, someone comes along in a couple months, they oil it up, different discrepancy model, just changed on it. Okay? All right. That's where I think we can kind of go with some of this stuff. So, you know, basically I've been talking about AX equal to B, and we're about ready to wind down on this. But here where the challenges lie. And we're not going to hit all of these today, but this is where I see where we have to think about, right? And these are all the practical things that you really have to deal with outside of this sort of model building I've talked about. One, you have limited measurement and data. In a lot of systems, that's the case. Some data is so difficult to acquire. You're trying to build a model, but the fact is you're not going to have a lot of data. Okay? Second, noise. Noise is always difficult. Multiscale physics. So we're really good at uniscale physics. The minute you start saying there's fast, slow, medium scales all together in there saying, it's very difficult. So you have to have a strategy around that. Latent variables. This goes back to if you measured it, doesn't mean the right variable. Latent variables are the hidden variables that are there, the ones that actually matter maybe. You might have actual measurements of some of the things that matter, but not all the things that matter. How do you discover those? Parametric dependencies. That AX equal to B assume that none of your parameters changed in time. It's going to be almost like you're just making huge assumptions about the existence of unicorns if you think you're measuring a system and it's not changing underneath you, right? A lot of systems you measure, like for instance in neuroscience, the system you're measuring, its parameters are wiggling around, and you're going to get the wrong model if you don't account for that. And stochastic systems. So okay, what I'll say here to finish up before we go to coffee is the two oranges we haven't really dealt with. So we have some ideas of maybe where to go with stochastic systems, limited measurement, we're still having trouble. But all the other four there, within this framework, you can develop workarounds. There are ways to take this basic AX equal to B architecture and imbue it with a little bit more extra widgets, mathematical widgets on it, to do things like discover parametric dependencies. We can do that. We can discover latent variable spaces. We know how to pull apart multi-scale physics, at least in simple systems, and we know how to handle noise. In fact, the noise one I think is one of the most important. That's where Sam Rudy finished his PhD with some stuff there. And I actually think he has just what's going to be a really classic paper on denoising a data using some of these ideas. So that's where we're going to finish now. Just to warm you up for part 2, to get you super excited during coffee hour so you just want to rush back. What if this was all a dumb idea? You know, I'm trying to discover nonlinear physics, right? What if I just could instead discover a better coordinate system where everything was linear? Okay, I'm going to let that sink in your head for a little bit. And then I want to talk about practicality of actual measuring systems. All right, let's go have some coffee. See you guys in a little bit.